Chapter 6 is a review from statics class, where you learned how to calculate the moment of inertia of various shapes. We solve stress and strain problems with axial loads, bending loads, and torsional loads using 4 pieces of information. The first type of information we need is the type of loading and position of the loads. The second type of information we need involves the mechanical properties of the material, such as Young's modulus and yield strength. The third piece of information we need is the length of the part. Finally, the fourth type of information involves properties of the cross-section, which include the area, the shape, the positions of the horizontal and vertical neutral axes, and the moment of inertia. You've seen moments before in statics class. We defined the moment of a force as the force times a perpendicular distance to where it acts. A wrench acting on a hex nut produces a moment P times L. We call this torque, but it's also a moment of a force. In general, the word moment means some quantity times a distance. The quantity doesn't have to be a force. It could be something else. Let's start with the rectangle at the left. Consider a small area that we will call lowercase a, which is located at distance y from the xx neutral axis. The first moment of area A is a times y. Remember, a moment is a quantity times a distance, so we can take a moment of a moment. So the second moment of area A is the first moment times the distance y, giving us ay squared. If we were to sum up all the little areas in this rectangle, along with their values of y, we would get the second moment of area for the entire rectangle with respect to the xx neutral axis. We call this I sub x, and the name that's been used since the 19th century is moment of inertia. If you take physics or dynamics classes, you'll know that the phrase moment of inertia is actually a property of a solid object that has mass. But we're using the term for a property of a cross-section that has no mass. However, this term has been used for so long that it's become a habit. As you look at the rectangle on the right, you see the same thing turn 90 degrees. The moment of inertia about the y neutral axis is the sum of a times x squared. Using the magic of calculus, we can add up an infinite number of infinitely tiny areas to come up with the moment of inertia of various shapes with respect to either the xx or y neutral axis. You can find these formulas for moment of inertia in Appendix C. Let's look at a practical example. A 2x4 timber has dimensions 1.5 inches by 3.5 inches. You can find the actual dimensions of timber in Appendix E. I sub x is 1/12 the base times the height cubed, which comes out to 5.36 inches to the fourth. This is a really strange unit. I can picture a length in inches, an area in square inches, and a volume in cubic inches, but I really can't picture anything in inches to the fourth. It doesn't have physical meaning, but it's a really useful tool for solving beam problems. You just have to take it on faith. I sub y is 1/12 the height times the base cubed, which comes out to less than 1 inch to the fourth. Why does this matter? Because bending stress in a beam is inversely proportional to the moment of inertia. A 2x4 is about 5 times stronger when it's standing on edge compared to when it's lying flat. This is why we place beams and joists on edge in home construction. It also matters when we calculate how much a beam deflects under load. Deflection is also inversely proportional to the moment of inertia. So a 2x4 standing on edge will deflect only 1/5 as much as a 2x4 lying flat. If and only if two shapes share the same neutral axis, then you can add their moments of inertia. They don't have to have the same dimensions or even the same shape. The only thing that matters is that they share the same neutral axis. These two shapes share the same xx neutral axis, so you can add their I sub x values. They don't share the same y neutral axis, so you cannot add their I sub y values. If the shape is hollow, and the whole shares the same neutral axis as the overall solid shape, then you can subtract moments of inertia. Here, the circle and the rectangle share the same neutral axis. Here's a more complex shape. It's not obvious where the xx neutral axis is, but if we use the transfer formula, we can find where it is and the moment of inertia. All we have to do is follow 10 easy steps. Step 1 is to divide the shape into simpler shapes. There is more than one way to divide it into rectangles, and here's one choice. Label the shapes by number. Step 2 is to calculate the areas of each shape and then enter them into a table. Add up the total area of all the shapes and enter that into the table. Step 3 is to select a reference axis. All of our construction lines will be drawn from this line. I like to pick the bottom edge. You could pick the top edge, and you'll get the same result. If you pick a position somewhere inside the shape, then the math gets messy, and I'm not going to show you that method. There are negative numbers involved, and I don't want anybody to be confused. Step 4 is to draw construction lines from the reference axis to the neutral axis of each individual shape. We'll call these distances y1, y2, and y3. In this problem, y1 and y2 are equal to each other. Enter the values into the table. Step 5 is to multiply each area by each y value. Enter the values into the table, and then add up the sum of a times y for all the shapes. Step 6 is to figure out where the neutral axis of the entire cross-section lies. The distance from the reference axis to the neutral axis of the entire cross-section is called y bar. It's equal to the sum of a times y divided by the sum of a. In this problem, it works out to 2.5 inches. Step 8 is to multiply a times d squared for each shape. When I make a mistake solving a moment of inertia problem, this is almost always where I make the mistake, by forgetting to square the d term. Make sure you solve for a times d squared, not a times d. Enter the numbers in the table and add them up. Step 9 is to figure out the moment of inertia for each individual shape. These are rectangles, so it's 1/12 the base times the height cubed. enter the numbers in the table, then add them up. Step 10 is the easiest step. Just add the last two entries at the bottom right of the table. The moment of inertia, the entire shape, is equal to the sum of AD squared added to the sum of the moments of inertia for the individual shapes. Each of the 10 steps is actually pretty easy, but putting them together in the right order can be complicated. The table will help you keep all the calculations in order. Make sure you draw all the construction lines on the diagram. It helps to draw it to scale so you can check if the numbers make sense. One thing you'll notice about this problem-solving method is if you make a mistake early on, it will cascade throughout the table and give you a really wrong answer. So it's important to pay attention to detail and check every calculation. What about I sub y? You have two choices with this shape. Either follow the 10 easy steps and solve the transfer formula the same way as before, but turn 90 degrees, or you can notice that the shape is symmetrical about the y axis. You can solve it faster by subtracting the little rectangle from the big rectangle because both rectangles share the same y neutral axis. Sometimes a compound shape has a hole in it. The 10-step process is the same, except that for the hole there are some negative terms. These include the area of the hole, anything multiplied by that area, and the moment of inertia of the hole. We define the moment of inertia of a shape with respect to the x and y neutral axes, where we added the sum of a times y squared for lots of tiny areas. In the torsion problems in Chapter 7, we need to add tiny area with respect to the centroid, so we define a new term, j, called the polar moment of inertia. It has the same units as the regular moment of inertia, units of length raised to the 4th power. You won't have to calculate j in the homework for Chapter 6, but you will see it soon.